Thanks, Joel. Hear me in the back? Or not? Good enough? All right. So, like Joel mentioned, I'm going to be talking about measuring dark matter in massive galaxies. This is work that I've done in collaboration with Aaron Romanowski, Gene Brody, and the Slug Survey. So, I'm interested in a basic question. What's the structure of a dark matter halo? And this is a question that's come up a number of times throughout the past few days. So I'd like to return to it. Because I'm an observer, I'm obligated to put in random negative signs in all of my quantities. So here I'm defining the inner dark matter density slope as being negative of the log density profile as we go towards R of 0. Here on the left, I'm showing you just a couple examples of what a dark matter density slope could look like. In bluish, greenish something, we've got a classic NFW halo with this gamma parameter of 1. And I'm contrasting this with an example of when we have gamma equals 0, when we have a dark matter core. And this is showing just this generalized NFW halo that we've seen. In the example I'm showing, we still have a density slope of -3 as we go out to the outskirts. So how do we find different cores or cusps, and where do they happen? What's the physics? As we've heard about earlier in Victor Robles's talk, this could be due to self-interacting dark matter or fuzzy dark matter, where we could get efficient core creation, that these mechanisms would be able to transfer energy into the inner parts of the halo. But we've also heard about how we could just as well get these kinds of effects through baryonic physics. We could have efficient transfer of energy through a rapidly fluctuating potential associated with bursty star formation. And this would be most effective on low mass scales, so in the dwarf regime. But there are other physical mechanisms that could create dark matter cores at the most massive regimes on the scale of galaxy clusters. And so you could just have dynamical heating as a result of merging that creates less cuspy, perhaps even cored halos for massive galaxy clusters. So if we want to try to disentangle any of these different effects, we're going to want a good understanding of how the inner dark matter density slope changes as a function of halo mass. So I'm giving you an indication of that relation, or at least some sense of our current understanding of this relation, on both the observational and theoretical fronts. So we see in gray some predictions from theory on different mass scales, going from dwarfs to galaxy clusters. And we see that there's probably some agreement here that we have a maximum of core creation down here in the dwarf regime, going up to cuspier and cuspier halos. And on the massive end, we have this trend that I mentioned that's probably due to dynamical heating during mergers. And that's where galaxy clusters tend to have less cuspy halos as we go up to higher masses. But the question that jumps to my mind when I take a look at this is, what's going on right in the middle in between these two regimes? What's happening to massive early type galaxies with halo masses between around 10 to the 12 and 10 to the 13 solar masses? And furthermore, why don't we have too many good constraints observationally in this region? So to explain why we don't have many good constraints at this point, and what we can do to fix this, I'll look at one particular galaxy, UC-1407, which is a massive early type galaxy, roughly at the center of a galaxy group. It's got a very low V over sigma, very low ellipticity. Looking at this image, it's basically a sphere. And using techniques such as the mass tracer estimators that Basola talked about earlier this morning, we know it's got a halo mass of around 10 to the 13 solar masses. So in order to try to get an estimate of what the mass of the halo is and how it's distributed, we're going to use dynamics. I'm going to make a number of simplifying assumptions here. For one, I'll assume that we have spherical symmetry. It's maybe not the best assumption, but it certainly makes my life easier. I'll also assume that our kinematic tracers are in equilibrium, so I can apply the Jeans equations. Even with these assumptions, we've got a number of challenges to deal with, and today I'll talk about two. So first, we've got the mass orbital anisotropy degeneracy, and second, if we want to know something about the dark matter halo, we better have a good understanding of where our stellar mass is, how it's distributed. So first, on the mass anisotropy degeneracy, we can define this beta parameter that really just gives us an indication of the relative importance of tangential motions and radial motions of a particular kinematic population. When beta is negative, we have tangentially biased or near circular orbits, and when it's positive, we have radially biased or plunging orbits going in and out of the potential. Point is that different orbital anisotropies give us different observed kinematics. And that's what we're looking at here. We see an example for very negative beta, very tangential orbits. We have a velocity dispersion profile that's rising. Whereas for the radial case, when we have plunging orbits, we've got a falling velocity dispersion profile. And all three of these cases were generated in the same potential. And so this is why you can easily mix up what the mass distribution in your galaxy is if you don't have a good understanding of this orbital anisotropy. So how do we deal with this problem? Basically, we throw good data at it. And in particular, we want multiple kinematic tracers of the potential that demonstrate different orbital anisotropies so that we can jointly model these together for one galaxy and then for a more robust mass distribution. So the data we use come from the Slug Survey. This is a spectroscopic and photometric survey of 25 nearby early-type galaxies. And a unique feature of this survey is that we have globular cluster kinematics out to, in some cases, almost 8 effective radii. Now, this feature is really important because we have to get very far out into the outskirts of the galaxy in order to get to a region where the dark matter dominates the potential. Here we're looking at a plot of the circular velocity as a function of radius, split up into different components of the mass. And so in orange, we've got the contribution of the stars, and in green, we've got the contribution of the dark matter. We see that the globular cluster kinematics probe this important region where the dark matter suddenly dominates the potential of the galaxy. Furthermore, we have overlapping stellar kinematics with the GCs. And what this allows us to do is to jointly model both GC and stellar kinematics in this region and get a much better understanding of how mass is distributed in that region. But we can even do better than that. We can add an additional tracer by leveraging our knowledge of the bimodal globular cluster population. So analogously to the Milky Way, many early-type galaxies are observed to have blue and red or metal-poor and metal-rich globular clusters. On the left, I'm showing the G-I color distribution of our spectroscopic globular cluster sample. And when we split based on color, we find interesting kinematic trends. So for instance, our blue GCs are observed to have a rising velocity dispersion profile, and our red GCs have a falling sigma profile. So this gives us an additional kinematic tracer population that we can use to beat down the mass anisotropy degeneracy. So challenge 2 is to understand what the stars are doing. So constraining the mass to light ratio is a critical hurdle to really understanding what this gamma, what this inner dark matter density slope is. Here I'm showing a result from POTA 2015, where we can see, and this is showing the covariance between the mass to light ratio and the inference on gamma. What we see is that when we don't have a good understanding of what the mass to light ratio is, we're unable to differentiate between a dark matter core and a dark matter cusp. There's just this very strong degeneracy that goes into effect here. And it's even a more subtle problem than that, because most dynamical models implicitly assume that the stellar mass contribution to the dynamical mass is just your enclosed luminosity times some constant mass to light ratio. But we know that for massive early type galaxies, there's often radial trends in their stellar populations. So this result from Martin Navarro et al. 2015 is demonstrating that there's a steeper IMF slope in the inner regions of this massive early type galaxy that then flattens out somewhat as we go out to the outskirts. And so this adds a significant systematic to the inference that we want to deal with. Fortunately, there was recent work on spatially resolved stellar populations by Vendakam, Conroy, and Vume in 2016 that showed that you could isolate where you have a bottom-heavy or more Milky Way-like IMF, and we can now use this to have spatially resolved mass-to-light information, and we use this information to infer what the stellar mass surface density looks like. And so now I'm contrasting that the stellar mass surface density with a variable mass-to-light ratio with that obtained from using a constant mass-to-light ratio. And so this does wonders for this challenge. So putting it all together, we use spherical genes modeling with multiple kinematic tracers. The dark matter model we use allows for either a cusp or a core, and the stellar model is constrained directly by these spatially resolved stellar population results. We constrain this on the stellar kinematics data and the globular cluster data we were looking at earlier. This is also showing our model fits. And the net result is we find strong evidence for a dark matter cusp in NGC 1407. We're effectively, at least with all of the assumptions that we've put in, we're effectively able to rule out a dark matter core. And so looking back to that relation of how gamma DM changes with halo mass, we see that this is roughly what we would expect for halos in this mass regime. Maybe it's a little lower, but we'll only be able to tell what the overall trend is if we're able to put more galaxies onto this parameter space. And so that's something that I've started to work on right now, is putting more slug slow rotators into this diagram. And we'll see if we're really able to connect these two mass regimes and see what the overall behavior of dark matter halos looks like. So I'll just wrap up and say that the challenges in dynamical modeling at the mass regime of early type galaxies can be better addressed by understanding your stellar population and through using multiple kinematic tracers. And massive galaxies like NGC 1407 probably have cuspy halos. So thanks for your attention, and I'll take any questions.
Well, that was a little bit early, so lots of time for questions. And do you have a question?
Yeah. Could you go back to the previous call?
Previous.
Yeah. So classes of galaxies, if you look at simulations, classes of galaxies are virgin, major mergers don't wipe out the cusp. The cusp is still good. Still the same 1 to 1. You can do simple exercise, simple n-body plots back together, and you see what happens with the cusp. It's still there. So it's not correct to put that virgin and all kind of the cluster.
For just a single merger, you mean? Can't destroy a cusp. I think
in simulations, virgins happen, and eventually at the end of the day, you have a cusp profile, which goes through all the virgin points.
okay, so you're talking after many mergers, you still have cusps?
Yes.
At the like 10 to the 14, 10 to the 15 with 10 to the 14 and 10 to the 15
Yes.
mass clusters?
It's essentially scale free.
Okay.
Don't matter.
That matters. In cluster galaxies profiles, last time I tried all the strong lenses, these temperatures with the cusp.
So, or I was just going to say, at least from my understanding of the issue, you just have, as you have these mergers, the normal dynamical friction that's causing these lower mass galaxies to fall in. Well, you've got the cooling on the satellites, but then you have a corresponding heating on the central one.
You see that the most dense ones, the central part of the merging objects, will be at the end, at the center.
Okay.
So they will be dense and cusp.
Mhm.
Simply without different physicality of bursty galaxy formation, you cannot wipe out the cut.
So the point of the paper that was referred to, which I'm a co-author of, is that it's the stellar lumps, not pure dark matter, that can be a heating mechanism. The other important heating mechanism that many people have seen in simulations is the effect of AGN. Very strong AGN feedback can drive gas out in a very short time scale. So it's a very simple, not merger, it's a different story. I didn't mention it, but it's very well known in literature that the AGN can, just as in small galaxies where star formation is providing a mechanism for rapid ejection of gas and basically a sudden approximation of releasing gravity. So also the same thing can happen in more massive galaxies when they're just forming. And that, in that case, it's due to AGN. And those two effects, the dynamical friction effect and the AGN effect, have been shown in many simulations to have this effect of smoothing out. So
Maybe we
the
can
question
talk
is really
afterwards
not
for
so much what happens at the 10 to the 13 halo mass, but rather at the cluster mass, why do they come down? And that actually wasn't the main subject that Asher was talking about. Are there other comments or questions?
Thanks, Joel.
Yes.
Have you thought to include some adiabatic contractions in your model? In that case, you would end up with something probably right.
So I haven't. I've begun to think about it. One interesting point on adiabatic contraction that came up is that just by, I was talking with Victor recently, and just observing a dark matter cusp at these mass scales isn't necessarily going to be enough to say rule out self-interacting or fuzzy dark matter scenarios, even though you would expect those to produce cores because of reasons like adiabatic contraction during the course of galaxy formation, where this region you would expect one of the major physical processes that could influence this core cusp would be the buildup of galaxies and that associated contraction of the halo. So I think it is important to model that carefully.
Other comments or questions? If not, let's thank the speaker again.
We'll leave.